Okay, so for this one I've been given a really complicated operational amplifier circuit. There's 1, 2, 3 op amps, and then 1, 2, 3, 4, 5, 6, 7 resistors. There is up here a 5 volt point, so basically they're saying like this voltage here is 5 volts. There's an input VI and output VO, and I want to figure out what VO is in terms of everything in the circuit including VI. So you could go up and put any arbitrary voltage in VI and then figure out what VO would be. The op amps as they're drawn, there's no power supply limitations. Like it's nowhere was I told, nor do I see little lines coming up maybe saying like 3 volts. So we don't need to worry about the implications of power supply limitation. Instead we can just focus on how would I solve this. So I go in and there's going to be, so let's try to look left to right, see any patterns, right? So we have VI. This goes into this. All right. You may notice what this op amp topology is. We'll come back to that in a second. Then this goes here. This goes all around. We have these two right here. This is at ground. This is at ground. So the first thing I usually do with op amps is I look and see. We know an important fact about them, that whenever they're negative feedback, which is oftentimes in our class, the two inputs are going to be tied together, and meaning they're like sort of brought together and they'll be the same voltage. So right here, for example, I know if this input, which is VI, that means this input must be VI as well. So that means right here must be VI. Okay, good. I'm just going to jump around and see if any of the other op amps have anything we can really add very easily. So on this op amp right here, both of these nodes, I don't have enough information right now at this point in my life to know what their voltages would be. So I know they'll be the same, but I don't know anything beyond that. Down here, I know again these will be the same. There's not enough information to specify what it'll be from this side, but if I look here, this node, the non-inverting input, is actually tied back to ground. So we know this will be 0 volts and this will be 0 volts right here. So this is actually going to be really helpful in a second. So we figured out, okay, these are tied together, this goes here. Another way you could have done that is just said, this is a buffer operational amplifier, a gain of 1, so whatever the voltage is here becomes the voltage here. Either way you arrive at that is fine. The next step I'll do is I now know that the node voltage here, and I know I'm actually using V's in here instead of the E's, but I just like to use V's a lot of times for voltages. But anyway, so we know the node voltage at this point in the circuit is VI. What can I do with that? So I think right away I oftentimes default and I'm like, I'm going to define some currents. So maybe I could figure out what this I1 is and this I2 and this I4 are. You have to be really careful at the outputs of op amps, because remember, they will do whatever they need to keep a voltage at what it's supposed to be, that the current out of them is unconstrained, right? So it's going to actually be very tough to set up a useful KCL equation. I think that's the toughest thing that people oftentimes deal with when dealing with op amps. So just be really, really careful. I don't know if a node equation is going to help me much here, simply because I can't, there's going to be too many things to solve for. It's not going to give me anything. So what I can do is I can look and say, okay, well, if I know VI, that's good. I could potentially figure out I1 if I wanted, because I know this is 5 and this is VI, so I could figure them out in terms of those two things. I4 I couldn't figure out yet because I don't know what this voltage is. Could I figure out I2? When I look at this, yes, I could, right? Because so far I figured out I'll have a voltage of VI at this point. The voltage on the other side of R2 is 0, so I2 is actually going to conveniently become just VI over 0. So I can write that down right here. VI over 0, VI over R2, excuse me. Cool. Now let's look at what this current's going to do. This current is going to flow down here towards the inverting input of the op amp. Now one thing we should remember is if we were to zoom in here on the op amp, right, we have this current coming in, right? There is no current going into the actual input of the op amp. So like right here, this must equal 0. All right, so that's actually really important, because what it's telling us is there's no current into the inverting input of the op amp. So all of that current must actually reflect up and go here instead. And this is going to be really useful because this is going to be able to tell us, I'm going to mark this as V, I don't know, let's do 2. Yeah, whatever, V2, just to keep it, because it'll look too similar to VI if I do V1. So let's call this V2. This is that whole electrical node right here. It's going to be really useful because now I know I have an expression in terms of inputs and constants for the I2 flowing down here. I know all of it will get kind of reflected or redirected down through R3. I also know what the voltage on one side of that R3 is, so I should, with Ohm's law, be able to figure out what this V2 will be, right? V2 will equal 0 volts minus this I2 times R3, right? And we know I2, whoops, let's do orange, can come from here, right? So really what we can say is V2 will equal negative R3 over R2 VI. So this is great. And actually, let me just write that here. Negative R3 over R2 VI. Super powerful. Now, what can we do with this? Well, we could go and figure out what the current through here is, you know, if I wanted. I could also, but at the end of the day, my goal, right, I got to keep my goal in sight. It's V out, or VO right here. How would I figure that out? The reason we couldn't go down this path initially before was because I didn't know the voltage is here, so I couldn't end up figuring out what VO is. But now I might be close to that, right? V2, we know what it is now. It's this thing, which is very helpful. Can we use this information to figure out what the voltage at the non-inverting input is? And we can, right? So again, remember, the current going into any op-amp input is 0. So this is actually going to be 0 amps right here. Now, if you have 0 amps going through a resistor, the voltage drop across that resistor is 0. That means that the voltage on both sides of this resistor must be 0. So the voltage here is going to have to be the same as what it was here. So this V2, I'm sorry, so V plus here will have to equal negative R3 over R2 VI. Right here. This is super convenient because now this voltage right here is what this voltage right here is going to be. So we can point that out in both spots. Good. Now we know the voltage on the side of this resistor, our VI. Now we know the voltage on the other side of that resistor, this thing, negative R3 over R2 times VI. So we can now go and figure out what I4 is, this original current which we couldn't solve right away. So let's do that. So I4, as I drew it, I4 will equal, I should zoom out a little bit, it's a little bit too intense. I4 will equal VI minus R3 over R2 VI all over R4. And we want V out. And so if we think about I4, it goes right here. It faces a junction. Now current could flow this way or it could flow up, but we know the op-amp prevents current from flowing into it. So all of that I4 is actually going to do the same thing as we saw before. It's going to flow up here. So this current I5 will be the same as I4. And this will be the last step in what we need to figure everything out, right? Because now we know the voltage on one side of this R5. We know we want to figure out the voltage on the other side, but we know the current through it, I5. So what we could end up saying is V out will equal the voltage here, which is negative R3 over R2 VI, minus whatever this current is times R5. And that current we have right here. It would be R5 over R4 times VI plus, I'm just watching out, these would have been plus before, R3 over R2 VI. And I believe that's all we need to figure this one out. And what's really weird, right, is did this 5 volts have anything to do with anything? And no, right? Our equation, which we generated, is this. I don't see 5 appearing anywhere in there other than as like a subscript in a variable. And part of the reason for that is actually because think about again where that 5 volts is existing and living in this circuit, right? It's 5 volts through a resistor into a node which is controlled by the output of the op-amp. Now the op-amp, its job in life is to, well, one of its many jobs, but it's basically saying the voltage here is VI. I don't care, it's VI. whatever current needs to flow into it or flow out of it to allow for that to happen, it will. And so this 5 volts is like, it's a constraint for sure, and it says, oh, the current flowing from here must be 5 minus VI over R1, but that has no bearing on the current that flows through here or even the current that flows through here. The thing that's, like, in terms of cause and effect, that's really leading to, you know, us solving the circuit is the fact that we know this node right here is at VI, because then that leads to us knowing the voltage over here, and then ultimately the voltage here, and then finally the output. So this is the value I get.